Well, good afternoon, everyone, and welcome to the SpaceX 3 Science and Technology Cargo News Conference. We have a panel here today to brief you on lots of exciting things that will be going up to the International Space Station, and we will start off with remarks and presentations from them before taking questions and answers. I would like to introduce to you the panel. To my left, Camille Alleyne from the NASA International Space Station Program Science Office. To her left, Michael Roberts, Senior Research Pathway Manager for the Center for the Advancement of Science in Space, which you may know as CASIS. And joining us by telephone from Washington, D.C., Andy Petro of the NASA Space Technology Mission Directorate. And we'll start things off with Camille.
Hi, good afternoon. Thank you so much for being here. It's our pleasure to join you to share a little bit about what's going on SpaceX tomorrow in terms of science. Tomorrow's SpaceX launch would contain just a little over 1,100 kilograms of research supplies that would support about 150 scientific investigations, both new and ongoing, that will be conducted during Expedition 3940. These scientific investigations will be conducted in the areas of biology and biotechnology, human research, physical science, earth and space science, technology demonstration and development, and education. Even though there's a lot of great science that will be heading to the space station tomorrow, I'll take just enough time today to talk to you about a few. The first investigation I'll share with you today is a new technology demonstration activity, which is designed to lay the foundation to send data back to Earth from the ISS at much faster rates than that is currently being done today. The OPALS investigation, and OPALS stands for Optical Payload for Laser Comm Science, was first conceived and developed by NASA's Jet Propulsion Laboratory, and is NASA's first payload that will demonstrate the use of optical communications for data transfer. Optical communication is an emerging technology that modulates data onto laser beams, and these laser beams has the potential to transfer data at much faster rates than currently is achievable with radio frequency transmission. This becomes really important for scientific instruments that increasingly rely on high data applications, such as high definition video streams. Once OPAL is delivered, it will be located externally on the ISS. As it orbits the Earth, it will make contact with ground-based receiving telescope located at Table Mountain near Jet Propulsion Laboratory, where a typical data transfer, such as video, will take place over a period of about 2 minutes while the receiver and OPALS are within line of sight. What you see here are images of the OPALS hardware taken as it was preparing to pack for launch. Currently, many of our deep space missions communicate at about 200 to 400 kilobits per second. OPALS will demonstrate the capability of up to 50 megabits per second, and I was told by the OPALS investigators team that this is analogous to upgrading your home system from dial-up to DSL. This is JPL's first external payload on ISS and its first launch on SpaceX. We're also launching the Vegetable Production System, also known as VEGI. And this is a plant growth system that will provide the necessary lighting and nutrients in which to grow plants in space. This system will be used for a wide range of purposes, from research to educational outreach, and also eventually as a potential food source, fresh food source for astronauts. The VEGI system will be the simplest plant growth system on ISS to date, and it will provide the greatest surface area yet to grow plants. We will start by growing red romaine lettuce, and I'm told by the investigator team that lettuce was chosen because of its excellent germination, ease and speed of growth, and its palatability. The lettuce will be grown on board the space station. It will be harvested and returned for nutrient and microbial analysis and evaluated for its suitability as a fresh food source for the astronauts. We have a prototype here in the media room, which the media is welcome to take a closer look after the briefing. The system can be deployed and stored as needed on ISS and can run on less power than is needed for your desktop computer. The plants are grown in these individual pillows that I have a prototype on the desk, and those act as pods of nutrients and root matting for the plants. In addition to the plant growth for producing edible crops, researchers are exploring future research that looks at the behavioral impacts of these plants in space, in addition to educational opportunities for students. The final investigation I'll mention today is called T-cell activation in aging, which is currently funded by the National Institute of Aging, which is a part of the National Institutes of Health, or NIH. The study uses microgravity as a novel and accelerated model system for aging to investigate mechanisms of the immune suppression commonly seen in the elderly population. Researchers will also like to figure out why the immune system of astronauts are suppressed in space. Our immune system protects us from disease, and the T cells are the first cells in the immune system to be mobilized when illness is introduced into our bodies. In a healthy immune system, T cells call on other critical cells which mount an immune defense against the invader. In past research investigations of this type, studies have shown that gravity affects gene expression and early activation of T cells in ways that are strikingly similar to the depressed immune system in elderly populations. Tomorrow, we will launch human T cells that will be activated once on board with simulated infections. They would be progressed over a period of time and returned home for analysis. Ultimately, the findings will be beneficial in new treatment strategies for immune system dysfunction. So again, these investigations are just a sample of the science that will be enabled by tomorrow's launch and that will contribute to the advancement of human space exploration and ultimately to improving the quality of our lives here on Earth. For more information on the science, please visit our website at www.nasa.gov/ISS-science and follow us on Twitter at ISS_research. Thank you.
Thank you, Camille. Mike.
Thank you, Mike, and thank you, Camille, for an excellent introduction of the science that NASA is supporting. We work at CASIS, work very closely with NASA to support very similar research aims. CASIS is the Center for the Advancement of Science in Space. We are a not-for-profit organization that works through a cooperative agreement with NASA to manage the International Space Station National Lab. The difference between the type of science and technology development that NASA continues to support and the mission objectives of CASIS-sponsored science going to station are essentially focused on the outcome of that research. The type of science that I'm going to describe in brief here that's going up on SpaceX 3 tomorrow is focused on science for Earth benefit. So we have access to 50% of the resources available to the ISS operating segment on station. And that enables us to reach out to communities that historically have not been able to access the International Space Station National Lab with ease. Those communities include not only academic investigators, but commercial companies who have interest in translational medical research or fundamental research in the life and physical sciences to go to station, as well as continuing to support other government agencies such as the National Institutes of Health that Camille mentioned in her introductory comments. So if I could have the first slide, please. So among several investigations that CASIS is sponsoring on the SpaceX 3 mission tomorrow, I'm going to highlight a few of those and describe in very brief detail the objectives of those investigations. Each of these investigations is part of what CASIS calls ARC-1. So ARC-1 is an acronym for Advancing Research Knowledge 1. ARC-1 is the first of several mission increments going to International Space Station that involve a multitude of investigators in different lines of investigation. Among those missions going up to ARC-1, to the International Space Station tomorrow, are 5 CASIS-sponsored investigations centered on protein crystal growth in the microgravity environment. I'm sure many of you are familiar with previous research that NASA has sponsored, as well as commercial companies have sponsored, in utilizing the unique environment on the International Space Station for prolonged precipitation of crystals. In these new advancements that CASIS will be sponsoring tomorrow, we have much better hardware and much longer exposure times for these investigations to be supported on the International Space Station. The potential outcomes of each of these investigations are going to have significant impact, we believe, upon many areas of medical research. I wanted to emphasize that each of these research investigations, many of them came to NASA through many different pathways. We are sponsoring investigations that are wholly sponsored by a commercial company, in this case Merck Pharmaceutical. Merck is sponsoring its own research to the station in the realization that they are going to be able to return better data from the unique environment of microgravity available on station than they were able to determine from crystalline protein structures precipitated here on Earth. We also have 5 investigations, 3 of which are going up on 4, that are going up on the ARC-1 flight on SpaceX 3 tomorrow, that came to CASIS through a solicitation. So CASIS has funding to provide to investigators who can access these funds through formal solicitations, requests for proposals. We have another investigation which is coming to us that Camille mentioned, the T cells in space, that is coming to us essentially through the pathway that NASA used previously, a NASA research announcement. In this case, that was actually funded by the other governmental agency that was interested in funding their investigators to use the national lab. In addition to these protein crystal growth experiments, NASA is also sponsoring an unsolicited proposal related to plant research, similar to the research that Camille described utilizing the veggie hardware. In this particular example, University of Florida investigators Annalisa Paul and Rob Furl are interested in following up some investigations performed earlier to look at the responses of plants at a molecular level to life in a microgravity environment. The unique environment of the International Space Station offers significant advantages for fundamental biological studies such as these, because all of life as we understand it evolved in a constant environment of 1G. There's always, as far as we know, been a constant 1 gravitational environment on Earth. When you study the responses of biological organisms in the microgravity environment, where you have altered the form of this 1 steady environment, you can actually uncover some significant changes in the responses of those organisms to many different environmental stimuli. Doctors Paul and Furl are going to use that environment to look at changes at the genetic level in gene expression of a well-characterized plant, Arabidopsis thaliana, in the microgravity environment. And as I mentioned, this proposal came to CASIS through the unsolicited portal. So in addition to formal grant solicitations that CASIS offers, where we identify an area of research that we are interested in supporting or which we believe has significant potential for Earth benefit, investigators can propose their own targeted areas of research to CASIS, and this particular unsolicited pathway is available to investigators anytime. If I could have the slide back up, please. Last is the T-cell activation and aging proposal that Camille mentioned. This proposal, this research opportunity began its life as a collaboration, a collaborative effort between NASA and the National Institutes of Health to enable access to the International Space Station to investigators who work at other government agencies. This partnership between NASA and the other government agencies has been very successful and has been utilized not only by investigators from the National Institutes of Health, but also by the USDA and Departments of Defense. In continuing to establish this relationship, CASIS is now going to take over the role and responsibilities that NASA formerly had in reaching out to other government agencies and introducing the unique opportunities available on the International Space Station to these investigators. If I could have the next slide, please. I just wanted to briefly touch on a few of the protein crystal growth investigators and the targets of their research that are going up on the SpaceX 3 vehicle tomorrow. Dr. Joseph Ng, who has a faculty appointment at the University of Alabama, Huntsville, and is also the CEO of iExpress Genes, is interested in forming crystals for his study on Earth that are much larger and much more homogeneous than he is capable of forming on Earth. His target in this area is to form a protein crystal that he is able to then subject to neutron diffraction studies. So unlike the typical X-ray diffraction studies that are used to study protein structure on Earth, neutron studies are able to locate at a much higher level of resolution and actually tell you the position of hydrogen atoms inside each of these protein structures. So in essence, Dr. Ng is interested in utilizing the unique environment of microgravity to get larger, more homogeneous crystals so that he can get higher resolution detail of the physical structure of a protein of interest to his research. In addition to Dr. Ng, we are also sponsoring investigations from Dr. Sergei Korolev and Dr. Pamela Borkman. Each of these investigators are interested in determining protein structure of proteins that are relevant to diseases of humans. So their studies will result in advancement of fields of research that are important to human health. So this again points out some of the differences between the type of research that NASA has sponsored in the past and continues to sponsor and what CASIS sponsors, in that we are primarily interested in sponsoring research that has direct Earth benefit for humans and other translational medical fields where the use of the International Space Station affords a unique opportunity for these investigators. If I could have my final slide, please. We're also sponsoring investigations by Dr. Aller and Dr. Edward Snell, who are looking at responses of multiple diseases and therapeutic targets and the design of therapeutic targets to aid in the development of treatments and therapies for these particular diseases. And last but not certainly least, I'd like to call out the research of Paul Reichert from Merck Research Laboratories, who is our commercial investigator, who is continuing on some preliminary research that he followed up on during the shuttle program to look at the capabilities of the microgravity environment for forming better crystals. In his particular case, Mr. Reichert is going to be looking at monoclonal antibodies to a specific protein formation in orbit. This will aid Merck in the development and completion of clinical trials for these particular therapeutic agents. Thank you, Mike.
Okay, Mike, thank you. And now joining us by phone is Andy Petro from NASA headquarters in Washington. Andy?
Hi, Mike. Appreciate the opportunity to join you all today. I'm going to be talking about two of the space technology payloads on this launch, the Robonaut legs and the PhoneSat. If we can put up the title chart to begin the presentation. The Robonaut is an example of how we can use robots for repetitive and dangerous tasks in space and how they can extend human presence beyond our own physical limitations. And the PhoneSat, a small spacecraft, shows how we can use these very small spacecraft and how they might eventually serve as a multitude of eyes and ears for observing the Earth and the universe beyond. So we can go to the next chart with the space technology portfolio. I wanted to provide just a context for how these two payloads fit into the overall NASA space technology efforts. On this chart, you see the 9 programs that compose the Space Technology Mission Directorate. Each of these programs has many projects. On the left, you see the Small Spacecraft Technology program. That's the one that sponsoring the PhoneSat, and as well as a number of other small spacecraft projects. And then the Game-Changing Development Program that is sponsoring the Robonaut, including the Robonaut legs. These programs, along with all the others, Through these programs, we work with private companies of all sizes, with universities, with NASA researchers, and independent inventors in our technology efforts. We can go to the next chart, the technologies for deep space exploration. I just wanted to mention the broad range of NASA technology development and highlight, for example, high-power solar electric propulsion, laser communications, advanced robotics, and lightweight structures. These and all of the other efforts we're involved with will enable the exploration of the solar system and improvement of life on Earth. And we can now go to the next chart about the Robonaut. The Robonaut 2 is the human-like robot that's currently on the ISS. It's been there since 2011. And what's there right now is just the upper body and the head. And that's been designed, the whole Robonaut has been designed to function within the same environment as the astronauts do. So it's able to function inside the space station. It's able to use switches and handles and tools just like a human astronaut can, which allows them to somewhat easily fit into the work that needs to be done in space. And the applications for this type of robot are, both inside and outside of the station, and eventually they could be used for satellite servicing, sampling asteroids, and other types of exploration work, along with the human explorers. And you can see in the photograph, the lower photograph, the Robonaut 2 on the space station, and it's currently mounted in a fixed position. And they've been running through a series of tests and demonstrations to show its capability to do a variety of functions. We can go to the next chart, which highlights the payload we're talking about, which is the zero-G legs that will be launched tomorrow and eventually unpacked and connected to the upper part of the robot. And these, we call them legs. Of course, they're not really for walking in the zero-gravity environment. They're used for climbing around. And the legs have 7 joints, and at the end, instead of feet, they have clamping devices that allow them to connect to handrails and other objects on the station and allows it to move around. And also then freeing the hands to be used for various tasks. And in a sense, this has been designed for a function in zero gravity that humans themselves have not really been designed to do, being able to use the feet as handholds and keeping the hands free for other work. I think we can go to the next chart. Just talks a little bit about what it'll be doing. Once it's unpacked, and it'll be connected to the upper part of the robot, as I was saying, and they'll begin testing its function in space, initially with an extension cord. Then a little later on, by September, it should have a new backpack for power that will allow it to move around independently inside the station. Ultimately, this is intended to be used even outside the station, where it might be even more useful because it can be doing work outside without having the astronauts needing to go through the difficult EVA activities that they normally do. So it's a step in that direction of a robot that can operate inside the station, outside the station, and ultimately do many, many other kinds of things as we explore space with them. So we can go to the next chart, which is moving on to the other payload, which is a PhoneSat 2.5. And this is a standard CubeSat. It's a 1-unit CubeSat, which means it's a 4-inch cube, weighs about 2 pounds. And this particular satellite is called PhoneSat because it's built around a smartphone as the computer and control system for the satellite. So it's a Nexus S smartphone, off the shelf inside, along with various other components, including 2 radios. The yellow tape you see sticking out the side looks like a tape measure because it actually is a piece of tape measure material. That's used as the UHF radio antenna. For launch, it's wrapped around as this is put into its CubeSat deploying container and then just pops out automatically once it's free in space. The little square you see on the top of the CubeSat is the S-band radio antenna. So this is the fifth of the PhoneSat series that have been launched just within the past year, and each one has had more and more capability. This one will be demonstrating the use of two-way communication with that S-band radio. It also has the ability to orient itself in space, and it uses, I think, a pretty innovative design using just 3 little electric motors. They're off-the-shelf motors that are positioned inside, and by turning them on and off, you can create a gyroscopic effect that causes the satellite to rotate to the position that you want. So it has three-dimensional pointing capability with this CubeSat. And in addition, it also has the smartphone camera on board, and we'll be using that to take pictures of the Earth, and we expect to get those back on Earth as well through the radio system. So we can go, you can of course see the size of, if I was there, I would be holding an example of it in my hand as well, but you can see it in the photograph. We can go to the next chart, which just shows the PhoneSat team. We're really proud of what this team has done. It is, as you can see, a bunch of young guys with just a few mentors. And they really originated this PhoneSat concept a couple of years ago. And in the past year, they have launched 4, and this will be the 5th. First one was launched last April. So we're really proud of what they've been able to accomplish and look forward to great things from them in the future. And we can go to the next chart because I just want to tie this into where this is heading, where we can take this very simple, low-cost satellite technology. What you see here is the Edison demonstration of small sat networks. That's our next mission, which will be launching in October. And this is using the PhoneSat heritage. Uses the same PhoneSat control system inside, the same wheels for the motors for orientation. It also has a science instrument. Each one has, and we're going to launch 8 of these at once, and they will be taking measurements, independent measurements, and then sending them to each other. Any one of the 8 can be the relay to the ground. And in the demonstration, we'll show that they can each take turns doing that. And that's a precursor for fleets of small satellites that might be used for science missions and other purposes in the years to come. Just wanted to mention, too, that in our program we have some other even more sophisticated demonstrations coming. We have a demonstration of laser communication, which will be the first time that's done with a CubeSat. And then also a rendezvous and docking demonstration with 2 small CubeSats, which will also be a first for that type of capability. And we can go to the next chart, which just shows really how this whole area of small spacecraft brings spacecraft development onto a human scale. You can see one of the PhoneSat team members assembling the Edison satellite. He's got the entire satellite in his hands, essentially. We don't need huge buildings, overhead cranes, and giant chambers to test them. This is all work that can be done more or less on a desktop. So it's a whole different scale of development, but it's something we think is affordable and rapid and transformative in its way. We can go to the last chart, and this is one of my favorite pictures. You can see 3 CubeSats. These are not ours, but others that are floating past the International Space Station. Our PhoneSat, of course, is going to be launched on the Falcon 9. It'll be deployed on the way up in orbit before the spacecraft reaches the space station, along with 4 other small sats that are also being launched. And this is through the CubeSat Launch Initiative, which is a NASA program providing flight opportunities for university and government payloads. But some small sats are also taken as cargo to the station and then later deployed from the station, and that's what's shown in this picture. And what's impressive to me in this picture is that you see just a portion of the space station, which is the largest satellite in orbit, and it's a satellite big enough for humans to live inside, and at the same time you're seeing some small satellites that are small enough to hold in the palm of your hand. So it's a pretty dramatic contrast. And I just want to finish with the idea that everyone is always, of course, interested in the next big thing. In our program, we're interested in the next small thing. So with that, I'll wrap it up, and I'll be on the line for any questions later on. So I'll turn it back to Mike.
Okay, Andy, thank you very much. And we're here ready to take your questions. Here at Kennedy Space Center, we have members of the NASA Social, in addition to members of the news media. So we would ask for you to please wait for the microphone, state your name and affiliation, and to whom you are addressing your question. And why don't we start right here in the front row?
Hi, I'm Ian Cluft with the NASA Social Group and also blogging for airlinereporter.com. Now, these CubeSats that are up there, this is, I've heard that they're, this is not just the only CubeSat. There's lots of them out there. How many of them are out there, and how many do you expect to make with this? And I guess that's for Andy.
Okay, if you can hear me. I don't really know the exact number. We're probably launching dozens of them collectively, the whole community, each year. We expect to be launching, in addition to this one, 10 more this year, and several in the following year, and of course more to come beyond that. It's something that's really taken off, both from the technology point of view as well as for science missions and other purposes. So it's a very rapidly growing field of activity.
Margaret Mason with the NASA Social Group, and this is for Alleyne. You mentioned that after the lettuce is grown, it's going to be returned to Earth for analysis of its nutrient value and everything. How will the lettuce be preserved from the time it's harvested, and what's the timeline for sending it back? Because we all know for food that we keep here on Earth in our refrigerators, it's not long before things have lost a significant portion of their value.
I was told by the investigative team that it will take about 28 days to grow the lettuce on orbit, and then it will be returned for the analysis.
So it will be returned when Dragon returns?
Yes.
Okay, thank you.
Okay, scanning the room. Does anyone else have any questions? In the back. Just give a moment to get to the mic.
Chris Haber with rocketstem.org, and my question is for everybody, whoever feels it's applicable to yourself. Could you talk a little bit about the future of the technology that you're flying today, once it's proven, how you want to develop it down the line in future missions, as well as possibilities for spin-offs?
Andy, do you want to try to answer that first?
Yeah, okay. And I guess I tried to allude to it a little bit in terms of the robot. Of course, the idea is that robots like this can become our partners with human explorers as we go out into the solar system, because they can do the repetitive tasks. They can do tasks in more hazardous situations than we might want to put people. And really the potential seems unlimited as to where they might be helpful there. And of course, there's a huge potential for applications on Earth as well, doing work in hazardous conditions on Earth, helping disabled people, all kinds of things like that. I think we see a lot of examples of that. And in terms of the small spacecraft, we also see a huge potential because we can produce them faster and less expensively, and in some cases they have even unique applications. For example, if you could put up large numbers of them for short-term missions in low Earth orbit, observing the Earth, we could get measurements around the Earth simultaneously in a way that you could never get with one big spacecraft. So, and we also see applications for them being part of deep space missions where they would fly along, be carried along with the larger spacecraft and then deployed when you get to the destination to do particular types of missions there. So I think that's how I would answer it.
Okay, Andy, do you?
Well, with respect to the payloads that are being sponsored by CASIS, there's direct benefit to the investigators and to humanity on Earth from the investigations focused on protein crystal growth, for example. So Merck is actually looking to form better crystals of a therapeutic agent, a drug. And from this investigation in flight, they'll be able to understand better the physical structure of their monoclonal antibody that's already in clinical studies. So this will translate in a very short amount of time to potentially significant findings that can benefit the use of this therapeutic agent to treat human disease. In the cases of the other protein crystal growth experiments that CASIS is sponsoring, they're actually looking at targets of potential human disease. In the case of the study that's being performed by Pamela Borkman at Caltech and her graduate student Gwen Owen, they're looking at the structure of Huntington's protein. Huntington's disease is a very serious autosomal dominant disease that afflicts many in the United States and the world. And that particular protein that is believed to be at the root of this disease cannot be precipitated on Earth because of its size and its ability to aggregate. So the actual action that causes human disease prevents its structure from being elucidated on Earth. So it's believed that the unique environment of microgravity will enable the formation of better crystals on Earth that will then translate to better structures. So those are just a couple of examples from the protein crystal growth types of experiments where the unique environment of space is going to translate very rapidly into potential technologies and therapeutic agents that have direct benefit from Earth. The research that I described on the plant science side of Annalisa Paul and Rob Farrell at University of Florida is looking at what is, on first glance, a very basic fundamental question: how do plants respond to the microgravity environment? But there's potential Earth benefit from that as well, because we need to understand how plants and all organisms respond to the microgravity environment, because with the removal of gravity as a constant, we get better insight into how the genes respond to different stresses that are placed on them. And that goes beyond plant science into basic understanding of how cells respond to that microgravity environment.
And just to piggyback on what Michael was saying about protein crystal growth and the use of microgravity as a unique environment to study these structures, there's a phenomenon that's gravity-induced called sedimentation, where heavy particles fall to the bottom, they fall towards Earth. And so on Earth, when proteins are grown, they have the distortion of gravity and of those particles settling. In microgravity, you don't have that gravitational element. And so your proteins tend to grow much bigger and much clearer, and you're able to study the three-dimensional structures of protein in a much more effective way than you would on the ground. So that's why microgravity becomes really important for protein crystal growth.
Okay.
I'd like to follow up with Mike. Have you, on the protein side of it, have you worked with the Stanford Folding at Home team on their distributed computing research on protein folding?
We haven't worked directly with them. As I'm sure you're aware, there are computational-based approaches to looking at protein folding, and they certainly give you very valuable insight in defining what, from a scientific perspective, would be called parameter space. So you get some ideas about what types of structures you can expect, and you can narrow down the field that you're searching, but you cannot get complete structures simply from computational studies. But certainly we have we have worked with the academic community, including Stanford, in defining the areas of research that we believe are important to the community. And we're certainly hoping to move forward in building collaborations between those who approach those problems from both the commercial side, who are interested in drug development, and those mostly in the academic community who are working from the target side with specific diseases, whether they're associated with aging, autoimmune diseases, or neurodegenerative and musculoskeletal disorders.
Okay, let's go to the phone bridge now where we have a question from Tariq Malik from space.com. Tariq?
Hello, thank you. I had a follow-up question for Andy Petro. Andy, I was just kind of curious what the timeline for Robonaut 2's legs would be, given a successful docking on Wednesday. How long would the crew have to wait before they unpack them? And just what are you hoping to see when it's all attached? A free-floating Robonaut? I'm just curious. Thank you.
Yeah, okay. I'd have to check with the team to know exactly what their schedule is. I know that through the next months, it'll be unpacked and attached. August to September timeframe is a big milestone where they will have the new backpack and be able to unhook the extension cord and allow it to move freely around inside the station modules. The idea is they won't free fly. It'll always be holding on to something, as a safety factor, actually. So it'll always be grasping a foothold as it moves around the station.
Okay, back in the room. Go ahead, please.
Yes, Scott Johnson. I'm with the NASA Social and also with Spaceflight Insider. This is a Robonaut question. I guess sort of from a historical perspective, what was the original thought process as far as making Robonaut in a humanoid form? Was that more of a practical thing, or was that more for public engagement because people relate to things that look like themselves, or was that driven by what works?
Yes. And I've heard that the project team describe the fact that working with something that looks a little bit more like us might be easier in some ways. But I think the biggest factor is just the practicality of having something that can work in the same environment, move through the same volumes, operate the same kinds of switches and other devices, work with the same tools, making it interchangeable essentially. In that sense, with the humans that are using the same system. So you don't need to redesign different interfaces for this robot. It can use what has already been designed for the humans to use.
Hayworth, I'm here with the NASA Social, and I'm a photographer with WeHadToday.com. It's a question for Camille. I was wondering if you could talk a little bit about the impact of the delays that this mission has faced on, say, the biological and the living tissue supplies that are going up for these experiments.
Yeah, they're very sensitive, of course, these biological samples, and have to be contained in a specific environment. So the delays do cause a little bit of challenges, and so we watch that as time goes along.
Go ahead.
Yeah, I'm Bill Jellin with the NASA Social and with MrExcel.com. The specific cell phone that's used inside the phone set, you said it was a Nexus. Do you have a model number? And how long will those last with the solar panels before they're not usable anymore?
Okay, yeah, it is a Nexus S phone, and it uses an Android operating system. As far as we expect them to last for the duration of the orbital lifetime, which in this case is going to be less than 1 year, but at least probably 7 to 8 months. The solar panels will recharge the batteries, which should allow it to continue functioning through that time period. So we think it's suitable for this, at least this kind of duration mission.
Okay, any final questions? Seeing none, we will go ahead and wrap it up. As you can tell, there is an awful lot of exciting science and technology about to go up into space tomorrow on the Dragon spacecraft powered by Falcon. And our next televised event will be the launch, which occurs at 4:58 p.m. Eastern Time. The launch of SpaceX 3 and NASA Television will begin our coverage at 3:45 p.m. tomorrow. In the meantime, you can keep up with all the occurrences on social media by following @NASA and @SpaceX and using the hashtag ISS. You can always keep track of the flight also on the web at www.nasa.gov/SpaceX. Thank you very much.